Okay, so let us continue. Okay, the third part of today's class. Okay, let us align at the equality sign. Okay, so next step. Okay, we can combine this term and this term into only one term. Okay, so we can delete it. Okay, delete it and and move this term outside of the parentheses and cancel. Delete j is not equal to m. Okay, then we combine these two terms into one term. Okay, so align at the equality sign again. Okay, good. Okay, this is equation 9. Okay, then substituting equation 9 into equation 8, we have, we can see that equation 9 is this equation, partial a over partial beta m is equal to 2 times summation I is equal to 1 to n xim summation j is equal to 1 to m xij beta j, and equation 8 is equal to partial beta transpose x transpose x beta over partial beta. Let us copy this. Which is equal to partial a over partial beta 1 to partial a over partial beta m transpose. So we have a partial beta transpose x beta over partial beta is equal to 2 times a vector. Column vector. So the last term is this term. And the middle term is the vertical dots. And for the first element, we only need to copy the last element. And change this m to 1. This is the answer. So next, it is equal to 2. We need to split this vector into a matrix multiplied by another vector. So how to do it? It may be a little bit difficult. Let us see. So first we need a matrix. And like this, and a vector. A column vector. So let us see. So here is xi1, I is equal to 1 to n. So we know that the first element of the first row of the matrix is xi1 with I replaced by 1. And the horizontal dots. And the last element of the first row is I is equal to 1 to n. So we need to change the first index to n. Like this.
Okay, and so on. So here is the vertical dots.
and here is the diagonal dots, and here is also the vertical dots. Okay, so times this vector. So this vector, the first term should be this. Okay, with I being placed by 1. Okay, so we replace this I by 1. Okay, 1j, and vertical dots. And the last element, we only need to copy the first element. Copy the first element and paste it here. And j is equal to, I is equal to 1 to n. So I should be changed to n here. Okay, n. Okay, like this. Okay, so this it is become xnj. Okay, and for the last column of this matrix, we can see that xi1 is changed to xin. Okay, so all we need to do is to copy x11 and change the second index to m. Okay, like this. Okay, and this is horizontal dots. Okay, and this is xn1, and with the second index being changed to m. Okay, like this. Okay, let us align at the equal sign, equality sign. Okay, next. Okay, 2. And we can see that this matrix, okay, x11 to xn1, x1m to xnm is equal to, okay, let me show you. Okay, x is equal to x11 to x1m and xn1 to xnm. Okay, so this it is equal to x transpose. Transpose. Okay, next let us split or decompose this vector into the product again of a matrix. Okay, a matrix and a vector. Okay, so let us see. The first term is summation j is equal to 1 to m x1j. Okay, so the first term, first element of the first row of this matrix is x1j, with j being replaced by 1. Okay, so this should be x11. Okay, and horizontal dots. Okay, and the last element is also x1j. Okay, with j being replaced by m. Okay, so it becomes x1m. Okay, like this. Okay, and so on. Vertical dots, diagonal dots, and vertical dots. Okay, and this vector is equal to beta j. Okay, the first element should be beta j. Okay, with j being replaced by 1. Okay, and vertical dots. And the last element is beta j, okay, with j being replaced by m. Okay, so like this. Okay. Okay, and we can see that this is x1j, this is xnj. 1 is replaced by n. Okay, so we can just copy this and paste here and change the first index to n. Okay, and horizontal dots, and copy this element and paste here and change the first element, the first index to n. Okay, like this. Okay, align at the equality sign. Okay, so we can know that it is equal to 2 times x transpose. Okay, and this matrix x11, x1m, xn1, xnm. Okay, you can see that this matrix is the transpose of this matrix, which is S transpose. So this matrix is equal to X. Okay, and this vector beta 1 to beta m is equal to, okay, let me see, beta 1 to beta m, okay, is equal to the vector beta. Okay, so it is equal to beta. Okay, align at the equality sign. And this is equation 10. Okay, good. So we have found 4 terms and reduced them to the simplest form in equation 1. So the finally the final step, substituting equation 2, equation 3, equation 4, and equation 10 into 1, we have, okay, let us see equation 2. Okay, equation 2. Okay, in equation 2, we have found partial y transpose y over partial beta is equal to 0. And in equation 3, we can find that partial y transpose x beta over partial beta is equal to x transpose y. Okay, so we can see that, okay, equation 1 is equal to negative x transpose y. Okay, and let us go to equation 4. Excuse me. Okay, equation 4, partial beta transpose x transpose y over partial beta is also equal to x transpose y. Okay, so we only need to add a factor 2 here. Okay, and finally equation 10, okay, partial beta transpose x beta over partial beta is equal to this term, okay, plus 2 times x transpose x beta. Okay, good. So this is the final result, and it is equation 11. Okay, so let us insert a black square here. Okay, and a line left. Okay, so we have complete deriving this equation. Okay, so do you have any questions? Okay, if you do not have any questions, let us go back to the handout of chapter 2. So in equation 54, this equation, okay, after a long derivation, we can find that this equation is equal to negative 2x transpose y plus 2x transpose x beta. Okay, finally setting the gradient of the loss to 0 and solving for beta, we get, okay, so set this equation to 0. Okay, so it implies that x transpose y, okay, this term is equal to x transpose beta. Oh, sorry, x transpose x beta is equal to this term. Okay, so let us solve for beta. Okay, let us multiply both sides of this equation by x transpose x inverse. Okay, then we get, okay, beta hat is equal to x transpose x inverse x transpose y. Okay, so this is the linear least square case. Okay, next let us look at the nonlinear least squares case. Okay, there is in some cases a closed form solution to a nonlinear least squares problem, but in general there is not. In the case of no closed form solution, numerical algorithms are used to find the value of the parameters beta that minimizes the objective. Okay, most algorithms involve choosing initial values for the parameters. Then the parameters are refined iteratively. That is, the values are obtained by successive approximation. Okay, beta jk plus 1 is equal to beta jk plus delta beta j, where a superscript k is an iteration number. So beta jk plus 1 is the jth parameter in the k plus 1th iteration, and the beta jk is the jth parameter in the kth iteration, and the vector of increments delta beta j is called the shift vector. Okay, this term. Okay, in some commonly used algorithms, at each iteration the model may be linearized by approximation to a first-order Taylor series expansion about beta k. Okay, where beta k is the parameter vector beta in the kth iteration. Excuse me. Okay, so f of xi beta, okay, it is equal to fk of xi beta. Okay, this term is the value of x of xi beta of the kth iteration, and plus summation j, okay, j is equal to 1 to n, partial f of xi beta over partial beta j, okay, times beta j minus beta jk, where beta j is the jth parameter. Okay, this is the first order Taylor series expansion. Okay, if you forget it, okay, please review the textbook of the calculus. Okay, so this term, okay, we can denote this term by Jij, capital Jij. Okay, so the Jacobian J, okay, we can see that it is capital J and is bold, so it is a matrix with ij's entry being equal to capital Jij. Okay, it's a function of constants. Okay, a function of constants. Okay, because Jij is a constant. The independent variable, okay, that is xi, and the parameters, that is the vector beta. So it changes from one iteration to the next. Okay, the residuals are given by Ri is equal to Yi minus Fk of xi beta minus summation k is equal to 1 to n Jik times delta beta k, okay, which is equal to Yi minus this equation. Okay, and let us denote this term. Okay, Yi minus Fk of beta, Fk of xi beta as delta Yi. Okay, and minus, okay, this term. Okay, the second term is equal to this term with k being replaced by small j. Okay, to minimize the sum of squares of Ri, the gradient equation is set to 0 and solved for delta beta j. Okay, this one, delta beta j. So negative 2 times summation n is I is equal to 1 to n capital Jij times delta Yi minus summation k is equal to 1 to m capital Jik delta beta k is equal to 0. Okay, it is equation 60. Okay, so let us see how to derive equation 60. Okay, let us see the blackboard. Okay, so I use the Microsoft Word instead. Okay, so this is chapter 2, page 47, and problem 48. Derive, okay, equation 60 in the handout. Okay, solution. Okay, so make it bold and make it bold. Okay, so according to equation 49 in the handout. Okay, let us see equation 49 in the handout. Okay, equation 49. Okay, the sum of squared residuals S is equal to summation I is equal to 1 to n Ri squared. Okay, so the sum of squared residual is, okay, S is equal to summation, okay, I is equal to 1 to n. Okay, it is 25 minutes. See you next time. Goodbye.